In February 1951, as a result of the findings of a Navy research program, proposal requests were issued to selected airframe manufacturers as invitations to bid on the design and production of vertical takeoff airplanes. In this design competition, Lockheed Aircraft Corporation was awarded a contract to build XF-V1 prototype aircraft. Analysis indicated that an airplane with a near-standard aerodynamic configuration would be best suited for the desired performance characteristics. Vertical takeoff airplanes have been made practical by the development of turbine engines capable of delivering greater horsepower per unit of weight. This vertical rising airplane combines the basic capabilities of the helicopter and the high-performance fighter. Consequently, it can perform many functions of both types and carry out assignments that neither one alone could accomplish. The original concept of the basic mission of the VTO fighter includes the protection of convoy vessels from hostile bomber attack. In a typical mission, assuming detection by surface vessel radar of 450-knot enemy bombers at a distance of approximately 145 nautical miles, convoy fighters execute vertical takeoffs and climb with military power to intercept the enemy at 35,000 feet and a distance of 50 miles from the convoy. After the attack, the XF-V1 can loiter in the area at 35,000 feet for approximately 1.5 hours. It then returns to the convoy to make a vertical landing. The landing transition is begun at under 500 feet to again bring the airplane into the vertical attitude with the wing pointed into the wind. The fighter then makes a straight descent to approximately 50 feet, executes a translating maneuver until directly over the landing area, and descends vertically. From a standing start at sea level, at design gross weight, the XF-V1 can rise vertically with an initial acceleration of 0.39 Gs and achieve a rate of climb of 10,000 feet per minute at 3,000 feet. It can climb rapidly to over 16,000 feet in a vertical position. Many different aerodynamic configurations were considered during the design development of the XF-V1. The configuration finally selected not only appeared to represent the best airplane to accomplish the mission and reduce development costs, but it also required no extreme pilot skills or radical flight techniques for hovering and transition. Because of the unconventional operational nature of the airplane, the testing program which led to the solution of all major problems was quite extensive. A 1/10th scale model was built to test transition, hovering, and low-speed flight characteristics. Also, high-speed tests were conducted to evaluate the performance of the airplane at Mach numbers up to 0.92. A 1/4th scale free flight model was constructed to confirm the results of wind tunnel tests. It was flown in the Ames Laboratory's 40 by 80-foot tunnel through the transition and hovering phase. This program again indicated that vertical takeoffs and landings could be satisfactory operational maneuvers. Additional models were tested for flutter and vibration characteristics, confirming calculations made in the initial phases of the design. For additional high-speed flutter data, scale tail surfaces were attached to high-velocity rocket. Recoverable cameras provided the primary means of recording airfoil behavior. These test vehicles provide a low-cost method for obtaining vital information. The model tail surfaces were accelerated into the transonic speed range at low altitudes where the air loads are the highest. Simultaneously, a wooden mock-up was employed to check assembly procedures and to study the application of manufacturing techniques, to confirm equipment clearances, and to work out maintenance features. A rotatable full-scale mock-up of the nose and cockpit sections was used to determine the degree of seat tilt necessary to supply maximum pilot comfort in vertical and horizontal positions, and it enabled design engineers to check visibility and control accessibility in all possible flight attitudes. With modern airframe manufacturing techniques fully utilized to accelerate production, actual fabrication of the first full-scale flight article began in February of 1952. Extensive use is made of integrally stiffened machine skins, and a one-piece extruded beam is employed for the wing. Manufacturing pre-planning and tool design is reflected throughout the prototype stages. For example, major airplane components subject to wear have been provided with simple interchangeable joints requiring a minimum number of attachments. The single beam wing was readily fitted to the fuselage. On its specially designed maintenance cart, the power plant was installed. Operational checks were made on the wing slats as well as the cockpit canopy. While the construction of the airplane was being completed, extensive systems tests proved the validity of the functional phases of the design. A full-scale wooden mock-up of the control system booster and its linkage was used to check out the translational characteristics. A complete control and hydraulic system mock-up was constructed using actual airplane parts. It is operable in both horizontal and vertical attitudes for complete examination of integrated performance. A full-scale fuel systems mock-up simulated operating conditions involving airplane attitude, altitude, fuel temperature, fuel flow, and simulated dives and climbs. At the company drop test tower, repeated drop test cycling was conducted to prove the structural integrity of the tail landing gear, the main auxiliary gear, and the tail auxiliary components. Shimmy tests on a rotating drum finalized the design of the tail auxiliary wheel. The wing, fuselage, and tail were subjected to a series of envelope proof tests on the static test airplane. Vibration tests were conducted on the actual flight airplane to confirm the calculations made in the early stages of the design. Proof and operating tests of all the control systems were also made. Drop tests with a full-scale static test airplane indicated the strength of the overall structure and provided further proof of the feasibility of vertical landings. The drops shown here in slow motion were made on 1, 2, and on all 4 wheels, up to design sinking speeds of 10 feet per second and angles of drop up to 12 degrees from the vertical. To provide additional protection for the pilot during flight, and more particularly during vertical takeoff and landing maneuvers, a series of tests resulted in the development of a completely automatic safety ejection procedure for the pilot. Phase 1 of this program was conducted to develop a parachute with very fast deployment characteristics. Chute drops were made from a helicopter flying at ejection seat velocity and an altitude of approximately 200 feet. In Phase 2, seat firings were made from the ground into a net. These tests, shown here in slow motion, were conducted by the Naval Parachute Unit at El Centro. The complete action takes place in less than 3 seconds. In Phase 3, seats were fired from atop a 270-foot cliff to check the operation of the complete system. Observe that separation occurs and the chute is deployed a considerable distance above the point of impact. These tests resulted in the perfection of a completely automatic shoulder harness and seat belt disconnect, automatic pilot and seat separation, and automatic deployment of the parachute. Although the XFV-1 is fully controllable by the pilot throughout all takeoff and landing maneuvers, an improved autopilot will permit automatic transitions from vertical to horizontal. Level flight to vertical, stabilized hovering, precision translation, and the automatic maintenance of any selected hovering altitude. Future tactical automatic flight control equipment will provide control for selected rates of descent and radar fire control for improved interception and engagement. Since the XFV-1 vertical takeoff airplane eliminates entirely the need for extensive airport facilities, necessary ground handling equipment will be furnished with each airplane. Only 3 major components are needed. An airplane handling cart rotates the airplane from vertical to horizontal or returns it to vertical in a minimum amount of time. In a horizontal position on the cart, the airplane may be easily maneuvered or towed to any desired location. The second item, an engine cart, is used for engine removal, and this same article is used for wingtip pod servicing when the plane is horizontal. The third component, a vertical service stand, is designed to permit servicing of the airplane in its vertical position. The design incorporates an offset, permitting exact alignment with the fuselage, and an upper platform is adjustable to desired working levels. As indicated by the ground handling equipment and operational characteristics of the airplane, only minimum terrain preparation is required for utilization of the XFV-1. It is therefore possible to operate from congested industrial or residential areas. In areas subject to attack, this could result in faster mass takeoffs, and underground storage and servicing facilities would greatly increase safety. Certain advantages of the XFV-1 are immediately apparent. The expense of building and repairing damage to large paved runways and aprons is eliminated. And due to disbursement and concealment, attrition is reduced. The unique capability of the airplane for basing near battle lines suggests the possibility for use in close support of ground attack operations. By the addition of RATO units, the XFV-1 could carry an overload of torpedoes for attacking enemy shipping. The airplane's relatively small size and vertical rising ability might be exploited for use as a submarine-based carrier of special stores. As operational experience accumulates, the XFV-1 may find application in photo reconnaissance, amphibious assault, specialized personnel transport, and other uses. On November 12, 1953, the first XFV-1 flight article moved out of its production hangar en route to Edwards Air Force Base. At Edwards, the plane and its power plant were readied for the initial operational tests. The propeller arrived November 19th, and its installation was completed November 21st. To provide additional braking and eliminate the possibility of ground looping during normal horizontal landings, the airplane is equipped with a drag chute in this configuration. XFV-1 design engineers believed that greater safety and training efficiency could be obtained by the use of a landing gear permitting both horizontal and vertical takeoff. Consequently, this airplane incorporates an auxiliary landing gear permitting conventional operation. However, even with the auxiliary gear installed, the airplane is still capable of making vertical takeoffs and landings. From November 28th through December the 2nd, 1953, the airplane was run through a series of taxi tests on the auxiliary gear. These tests indicated completely satisfactory function and controllability. On June 16, 1954, the initial free flight program began. These tests will determine the operational capabilities of the XF-V1 and gain pilot experience toward transitional and vertical flight in the near future. The XF-V1 indicates the promise of a new concept of aerial warfare in providing an array of protective fighters over a selected area without flight or facility delays.